So we're moving on from the last section, and at the end of the section, you were asked to complete this table. Right? You were asked to complete the table given the parameters that you would already calculated, which was the torque, bending moments, and in the previous video, we saw how we got the stress concentration factors. So I will start at position A. At position A, we identified that there were three actual positions that is of concern. We have on the left-hand side where we have a circlip, and we have a retaining ring groove, and we said that the stress concentration factor at that point was 3. Right, so if you look at position A, D1, right, so A is the position along the shaft on D1, the number D, that represents diameter 1. So we're looking at this one section, but there's the possibility of 3 minimum diameters due to 3 different features on the shaft. So that's why we have D1, D2, and D3. So D1 is where we have the circlip. We said that the stress concentration factor is 3. Right, so let's back up here, go back to the torque. We recall that the torque flows in through the key, through the gear, through the key, flows to the right hand side and flows out at gear C. Right, so on the immediate left of the gear, we said that there is no torque flowing at that point. So that's why we have the torque here as 0. For MZ, MZ is the bending moment in the XY plane. So if you look at A, point A in the XY, the bending moment is 0. My in the XZ plane is also 0. So M, which I asked you to calculate a couple of questions up, is actually the resultant, which is the square root of mz squared plus my squared. Alright, so if you look at the shear force at position A was minus 9340, and in the z direction is 3398. So again, the resultant shear force would be the square root of vy squared plus vz squared. So that will be v. Right, we identified that kT was the stress concentration factor due to the circlip or the retaining ring groove, which is 3. And over here now, which we did not ask to complete, which is new in this video, is the equations to calculate the minimum diameters. So those are these equations here. So dmin from equation 1 is this equation that uses the shear force alone for calculation of the minimum diameter. And dmin, which is equation 2, is a bigger equation that uses both the bending moment, the resultant bending moment, I should say, and the torque flowing through at that point. Right, so because the bending moment resultant is 0 and the torque is 0, of course the dmin, the minimum diameter calculation from equation 2 will be 0. The resultant shear force, however, there is a value which is 9938.9, so you will get an actual value. So from at this position on the left hand side, position A, D1, that is, the minimum diameter that will be required for the safe operation of the shaft at that point is 28.6 millimeters. Right? Now, next we go on to the middle. So the middle is where we have the key. Now again, the shaft, the torque is flowing through at that point. So therefore it will have the torque that we calculated. Because it's point A, the bending moments are still 0. And the shear forces are the same. The stress concentration factor for the key we established was 2. So now that we have a torque, we will actually have an equation. That is, we will actually have a value for dmin from equation 2. So you could see how larger that value is. Now it's 41.8. And then we move on to D3. Again, D3, the only difference is now than position 2 is that we have a different stress concentration factor. So you could recall in the video that I said that there's no need really to do the equation twice because, of course, because you have a higher stress concentration factor due to the key, then it doesn't make sense to calculate this position where we have the shoulder, but I'm doing it just for the sake of completion. And also it's on Excel, just dragging on the equations, so it takes no effort really. So this way you could actually see everything. So you put down everything and you'll see everything. Right, so you could see here that of course the diameter is the minimum required diameter is the same. Again, that's because even though the KT is different, KT multiplies by M, and M is 0. So this term has no effect, then the KT has no effect. Right, and now next we go on to position B, and we said at position B, Again, the torque is flowing, so we have our torque calculated. Now at position B, now we actually have a bending moment. Right, so that would be minus 2,371 and 863. Right, we have our resultant, we have our shear force. So notice our shear force is neither 1120 or 9340. It is the actual height on your shear force diagram, which is 2540. Right, so that is the actual value, by the way, of the reaction in the y direction. Similarly, VZ in the z direction, the drop down here is 239. So you have your resultant. Right, we said that it is a well-rounded fillet, so the stress concentration factor was 1.5. Right, so again, we just have equation 1 for completion's sake, but you could see how larger the effect of equation 2 is when we consider the bending moment and the torque. So that is 71.6 or 71.7 millimeters. Moving on to position 2. Now remember, in the end of the video, the prior video, I said that they made an error in putting this keyway here. So what we're looking at is the fillet on which the bearing is resting. We say that the bearing is press fitted on, and it bounces the shoulder and remains in that place. And that shoulder, the stress concentration factor is 2.5. So the values again are the same because it's the same position B. And we say the torque is flowing through everything, so that's why we have the torque is the same. The stress concentration factor is higher, and you could see the value we have there is 0.846 or 84.6 millimeters. Next, we move on to position C. Again, it is the same story, going to position C. Now, when you look at the right-hand side, D3 position, we said that again the torque flows through and flows out at C. So the circlip or the retaining ring groove on this side of the shaft now experiences no torque. So we have torque is 0. But the bending moment is still there. The shaft is still bending and experiencing bending moments. So we look at the bending moment at that point 1897, and in the y direction it's 1381. Right, and then we also have our shear force. Our KT value for D3 is 3 because it's a retaining ring groove. So even though we don't have any torque flowing through, you could see because of the high stress concentration factor, our largest minimum diameter is 87.6 millimeters. So out of these 3 diameters calculated for point C, the one that we will have to use, or the minimum diameter that we have to suggest, would be 87.5. Right, even though the torque is 0. So in this case here, the torque does not dominate the design, it's the stress concentration factor that dominates the design. So it's something to note when looking at retaining ring grooves on a shaft. And sometimes it might even be suggested to look for an alternative way to affix the gear to the shaft and prevent it from actually moving laterally. The last one is at D where we have the bearing. So again, there's no torque, and also at the end there the bending moments are 0. So the only thing we're dealing with here is the shear force. So of course the bending moment equation 2 will be 0, and then you have your shear force here. Right, again it's a sharp fillet, so the KT value would be 2.5. Right, so this is the table completed. Right, so you will have to do this procedure for design practice 3 and also the assignment 3. Right, so if it is you want to enter these big equations one time, go right ahead, and that way you could actually use this to test your chart. And once these equations are working and your table is working, then you could actually use this chart now for the other shaft design questions that we'll have to do in design practices and the assignment 3. Right, so after looking at this video, then you could proceed on to the next section where we have to determine the bearings.